Welcome to Innovate and React. I'm Kevin Hares, and today's episode will be about possible solutions for the hydrogen economy. We need more hydrogen than we can produce, but transporting hydrogen as a gas is also not trivial. This is where ammonia comes into play as a hydrogen carrier. And today I'm with Malte Behrens, who is a professor for inorganic solid-state chemistry at the University of Kiel in Germany. And one of his topics are catalysts for ammonia decomposition. Welcome, Malte. Thanks for joining me.
Yeah, thanks for having me, Kevin.
Yeah, I'm glad you're here and sharing your insights into this very interesting topic. But let's maybe go back first a bit. What brought you to catalysis?
Yeah, so my journey to catalysis was maybe not so straightforward because in my studies here, which I also did here at Kiel University, catalysis was not a big research topic, and also maybe not the biggest topic in teaching. And so I got my training in solid state chemistry, and I was always interested in solid state chemistry in those days. These are the early 2000s, were to some extent about finding new compounds, new crystal structures, like a field of applied crystallography, finding new materials. But I was always a bit more interested in properties of those compounds, of those materials. And I was lucky that in the group of Wolfgang Bench, where I was working, he was also like taking this maybe a bit more modern view on solid state chemistry. And we were dealing a lot with reactivity of solids, but not with catalysis. This was intercalation chemistry. So maybe there was a relation to battery research, but it was more on a very fundamental level. So we looked at like how magnetic properties changed when, for instance, lithium ions are intercalated into transition metal chalcogenides materials. And that was all interesting, but I always thought, okay, I would wish to work a bit more on problems that are maybe a bit more on the applied side, nevertheless looking at fundamental aspects of those. And it was like in the middle of my PhD thesis when we wanted to use X-ray absorption spectroscopy, which was a new technique at those days for me. And I was going to a workshop at the Fritz Haber Institute in Berlin because one of the group leaders there, Thorsten Ressler, in the inorganic chemistry department, he developed a program that we wanted to use, and he was inviting everyone for a workshop on how to learn about this program.
The program was for analyzing something, or?
Yes, for evaluating those X-ray absorption spectra. This was the WinXAS program package which we used in those days. And Thorsten Ressler made this workshop at the Fritz Haber Institute where he was employed in those days. And that's, of course, a hotspot of catalysis science. And it was like a mixture of, the fascination of catalysis science. And most of the examples that Thorsten was teaching in those workshops were from catalysis. But also it is a very unique place, I believe, with this, going back to Fritz Haber himself and this very nice surrounding in Berlin-Dahlem. So I was really fascinated by that. And somehow I thought, okay, well, this is probably a good place to do a postdoc and to go there as a next step of my career. And that's what I did. So that was also one reason to go into heterogeneous catalysis. Then I joined the department of Robert Schlögl, who was also very inspiring in those days as a postdoc. This is how I came to catalysis, with a background of solid state chemistry, then dealing with the synthesis and with also analytical problems of those nanostructured materials.
And now you're combining both.
Yes, this is what we're trying to do, to take a materials-focused perspective, I would say. So we're not reaction engineers. We are not working on the optimization of processes, but we want to develop new and also optimize and make better and understand the challenges and the limitations of catalysts and also of applied catalysts. We are doing synthesis. The idea is to synthesize not a single material, but a series of samples in order to be able to look at trends, structure, activity correlations, composition, selectivity correlations, whatever, any of those correlation is interesting for us. And we have, in the first approximation, an empirical approach to that. So we want to start with a material that has that is high performing already, so that has some relevance. And then we want to modify it in a most controlled manner possible and see what effect this modification had on the kinetic properties of that material. And from that, we hope to get some understanding. And then with that trend, we get a working hypothesis. It's typically necessary then to team up with other collaboration partners, more from model catalysis or particularly also from theory, in order to, test and validate such hypotheses. I think that those correlations are a very inspiring source of these hypotheses to better understand how a catalyst is doing what it does.
Basically also doing the reaction optimization where you would usually look at different parameters and you're looking at the composition of the solid material and then change some parameters of the material and then see what this change has an influence on the reaction you're looking at.
Exactly. What is important, also look at maybe less performing samples. So it's not a pure optimization research, right? But we want to get a certain parameter space that we then are confident at some point in time that we can control, say, the activity with that parameter. And of course, like a more or less trivial parameter would be the specific surface area of the active metal. If we talk about metal catalysts, it's always good to have as much surface area available, exposed as possible. That would be one aspect. But also there are more involved things like catalyst promotion, for instance, adding a little bit of additives in exactly the right amount at exactly the right place in the sample that determines the final kinetic properties of the material to a large extent. And that is less easy to understand than just saying, we need more metal surface area in order to get more active sites, which also is a very important thing, of course.
And also find trends instead of trial and error for each and every sample, I think is an interesting approach.
This is also where we just started to dive into that. Data science approaches are very powerful, or have become very powerful, I believe. Because, as I said, for those trends, also samples that are maybe on the first sight not so interesting because they are not performing better, they still can be very valuable for understanding and describing the trend. That is, so why are they not better? Yeah. And that information can always also lead to new insight. That's something that is, I think, this approach will in the near future probably be more and more governed by these data science approaches and the tools that we now have available.
Yeah, for that you always need a larger data set than just a few samples.
Exactly.
And I think that's very interesting because all this high throughput catalysis research, which basically started with the invention of the Haber-Bosch process. I had also a previous episode about the history of the Haber-Bosch process, and there they tested an extremely large amount of catalysts and then eventually found the catalyst that is still mostly used today, so almost 100 years ago, but they did such great work that it's still applicable. Yeah, and you have also been at the Fritz Haber Institute.
I mean, the ammonia story, of course, is very well present in the history of the institute. Although I think that Haber did his major experiments in his time in Karlsruhe before he came to Berlin. Nevertheless, and there was also coming more from a maybe remote university in Germany to Berlin. It was my second year as a postdoc there. In 2007, it was when Gerhard Ertl got the Nobel Prize. And that was also, of course, for his work on the fundamental work on the understanding of the mechanism of the Haber-Bosch process. So that was, of course, for me as a young scientist, very, very exciting anyway, but also very interesting to see that the direct line from Fritz Haber in early 20th century. And then decades, I mean, it was almost 100 years ago, although the work from Ertl was a bit earlier than when he received the prize. But decades later, there was the knowledge about the reaction mechanism. And it is exactly what you say. There was this tremendous effort of an early version of parallelized or high throughput materials testing by Alvin Mittasch in the early 20th century. And the result is super impressive, right? This catalyst is still, as you already said, with only little modification in operation nowadays. And then it took another, 50 years or so to really understand all details of the reaction mechanism. And it shows us that, of course, fundamental understanding is important and is the goal and is needed. But on the other hand, whenever this knowledge was available, it didn't directly create a new breakthrough of a new catalyst, right? It was not like, okay, wow, now we understand and we know what to do in order to further improve the catalyst. So the old work of the Alvi-Mittasch lab is still, stands for itself.
Yeah, and now we can also use this knowledge about the mechanism of the ammonia production and to some extent gain knowledge for the reverse reaction for the ammonia decomposition, which we also need nowadays as a new phenomenon. But maybe for those listeners who are not familiar with this problem, why is it so interesting to use ammonia as a hydrogen carrier?
Yeah, I think there are two major aspects. The one is it is carbon-free, so there is no coupled product of CO2 anywhere when you release hydrogen from ammonia. We need to talk about the carbon footprint of the synthesis of ammonia, of course, but for the hydrogen release itself, there is ideally no other molecules involved than hydrogen, the target, and the completely harmless dinitrogen molecule. That would be one aspect. And the other aspects, I believe, that is important is that the transportation and distribution of ammonia is so much more facile compared to pure hydrogen. So, of course, any chemical conversion is lowering the overall efficiency of the energy that is used or that is put in those molecules. But I think here it really can be justified by the fact that you need only 8 atmospheres in order to liquefy ammonia, and in a liquid state it can be transported with existing technology, and it is transported already, right?
It's a commodity.
It is a base chemical for fertilizers that is globally shipped around the world without problem. We have that technology under control, which is not yet the case for pure hydrogen because of its high volatility and maybe also the dangers involved, the low temperatures, the high pressures that is needed in order to tame hydrogen in a way that it can be handled and transported. I think those are probably the two most important aspects on why ammonia may not only be the basis for artificial fertilizers, but also for at least some part of the energy sector.
And also interesting is that low volumetric energy density of hydrogen, that in a tank of ammonia you can actually transport more hydrogen than in the same tank if you would just have hydrogen in it. So that's also a big advantage when you want to cover large distances. For smaller distances, like pipelines are the way to go. But for example, if you want to import hydrogen from Brazil or Australia or Saudi Arabia, then these distances are too long for pipelines, and then we need hydrogen carriers. Yeah, and to use ammonia as a hydrogen carrier, we not only need to synthesize this, we also need to get the hydrogen back from it. It's a technology that a lot of bigger companies say they could do it very quickly, but there are so far no large-scale plants available. So what are the challenges in the ammonia cracking or ammonia decomposition?
Right. Yeah, in fact, that's another advantage, right? I would also agree that the ammonia cracking or decomposition technology is available already. As with any technology, of course, you want to and you need to design it in a way that it is most efficient, right? To get the most revenue out of it and to be most energy efficient in the end. And that also will of course determine to some extent the price of the hydrogen in the end. So it's still, of course, needed to further improve and to research this project. And of course, as I said in the beginning, we are doing this from the perspective of the catalyst to find the best possible catalyst. But I would agree it's probably not a major showstopper to say, well, mankind is not able to decompose ammonia. This should be possible, but there is no, so far, as you correctly said, there is no industrial process, because also there was no industrial need, right? The utilization of ammonia was for fertilizers, so you wanted to synthesize it and not to decompose it. And although it would be possible, and there probably also would be catalysts available, there was only little or only niche application of that as a process. I know there are some companies that if you want to operate fuel cells in very remote locations, you can also have an ammonia tank there and do the ammonia decomposition on site in order to fuel the fuel cell with hydrogen, but it's not, like that would be a miniaturized version of what we're talking about, but it's not the large scale process that is envisioned in terms of using ammonia possibly as an import vector for energy into Germany, for instance, right? Then those larger plants would be needed at sites where ammonia, harbor sites, for instance, where ammonia is imported. And then we can think about a distribution net for the hydrogen from those places. But the ammonia decomposition process itself, I would say, is possible, is known. It was studied a lot, mostly also because the whole field of model catalysis that is typically not easy to implement the high pressures that you need for ammonia synthesis. They contributed a lot also to ammonia, to fundamental mechanistic work, but mostly also by looking at the formerly reverse reaction, because the conditions were just not right in order to conduct ammonia synthesis. So it's possible. We have a catalyst, but we may need better ones.
So they looked at the reverse reaction because they could not perform the high pressure for the ammonia synthesis, but since it's an equilibrium reaction, they looked at the reverse reaction.
This is what happens. What happened in the second half of the 20th century, for instance, where surface science studies contributed a lot to the understanding, and that is based on what is called the concept of microscopic reversibility. Saying that the elementary steps of the forward and the backward reactions should be the same, just in another order, in the reverse order. And many of those elementary steps have been researched also by not feeding nitrogen and hydrogen into whatever reaction chamber, but by feeding ammonia and then looking at the intermediates that you have at the surface. You just approach those intermediates from the other side, and then you get them in a higher coverage compared to if you try to synthesize those from hydrogen and nitrogen, but at maybe too low temperatures and for sure too low pressures.
Oh, interesting. So why can we not just use the iron catalyst in the Haber-Bosch process to use it for decomposition?
That's a good question, and I would say, first of all, it could be used. It is active, but is not the best catalyst. And this is more or less a breakdown of that concept of microscopic reversibility, which is in principle only very true if you look at forward and backward reactions at exactly the same reaction conditions. But if you do ammonia synthesis at 200 bar, and you look at ammonia decomposition at 1 bar, then that has an effect on the chemical potentials in the reactor, obviously. And those also would affect the catalyst. And that's a manifestation of catalysts being dynamic to some extent. So they develop their active structure often only in contact with a reactive medium. If that is ammonia, in ammonia decomposition, there is a high partial pressure of ammonia because that's my feed, at least in the early part of the catalyst bed, if you think about flow reactors. And that will easily lead to nitridation of metals with a very strong binding to nitrogen.
So forming metal-nitrogen bonds, and then the nitrogen is fixed.
Exactly. Metal nitrides, iron nitride in this case, is formed at high ammonia partial pressure in ammonia decomposition. If you use the very same catalyst for the equilibrium limited ammonia synthesis reaction, you will not reach high ammonia partial pressure, right? The limitation is at below 20%, maybe around 20%, and you will not get more than that at the conditions where a typical ammonia synthesis plant is run. And that partial pressure is typically not enough to nitride the Haber-Bosch catalyst. So the same catalyst forms an iron nitride in ammonia decomposition and is iron metal in ammonia synthesis because of the difference in the partial pressure of the feed that you have, or of the ammonia in particular. Now, what we also looked at, also with the help of a theory, a DFT partner group at KIT, the group of Felix Stutt, is that if you now consider the reaction mechanism of ammonia decomposition in what we call like a Langmuir-Hinchelwood mechanism, you absorb the reactants, they react in their adsorbed state at the surface, and you desorb the products again. And if you compare now an iron metal surface and an iron nitride surface, you will find out that the iron nitride is less active.
Because the metal sites are blocked, or?
Well, the metal sites are still there. It's still active. You still can also in metal, an iron nitride would expose iron atoms at the surface. But I think in simple terms, you can think of the iron is already surrounded to some extent by nitrogen in its bulk. So it's maybe less prone to absorb nitrogen from the atmosphere. It's already, say, iron is already in a happier state than if there was less nitrogen around it, and that lack of metal nitrogen binding of a nitride compared to metal is detrimental for the catalytic turnover. So we get lower rates on iron nitride, and that was also one starting point for a research that we did recently. That was then looking at a way to prevent nitridation of iron by changing something in the catalyst. And it turned out that, for instance, alloying iron with another metal that is not a typical nitride forming metal, and we looked at cobalt in particular, that this indeed helps to prevent the bulk nitridation of the iron. So the surface iron is then surrounded by cobalt and not by nitrogen. Cobalt itself is also not a good, not the ideal catalyst for ammonia decomposition, but those iron catalysts that are then, they can withstand the nitridation because they have already their bonding partners in the cobalt. Cobalt itself is not nitrided, and that makes those iron atoms as active or highly active in ammonia decomposition.
So a combination of both.
Yes.
Properties, so that the iron is good at the reaction but likes to take up the nitrogen and be nitrided, and the cobalt is not as good in the reaction but it doesn't form the nitrides, and then in combination you get a higher activity because there are no nitrides formed, but still the iron can perform the reaction. Exactly.
And this is also, we confirmed recently in a collaboration with another theory group that really looked at the kinetic barrier of the nitrogen at the surface to go subsurface, to go into the bulk and form a nitride. And that was limited to a large extent by the presence of cobalt in the catalyst, which makes the nitrogen coverage at the surface higher. It does not go subsurface, but it can react and it can form nitrogen. Because the recombinative desorption of the dinitrogen is in very many cases the rate determining step.
Okay.
So we are interested in the hydrogen, but we need to learn how to form nitrogen on those surfaces, because making hydrogen is easy, but more or less, but it's coupled to the formation of the nitrogen-nitrogen triple bond and the desorption of that molecule. And that is a challenge in this type of catalysis.
Interesting. I thought that the formation of nitrogen is always favored because of its triple bond.
Yeah, thermodynamically, it's an endothermic reaction, right? So you need high temperatures to do it, and then it is kinetically difficult to get the two nitrogen atoms in the correct positions on the surface in order to form that bond. And that one could say again is, you can look at it with this already mentioned concept of microscopic reversibility, because that is of course the very prominent challenge in ammonia synthesis. You want to split it. But in fact, the energy barrier on the way back or forth is not so different. So it's also a problem if you go the other way around, because you also need to go over a similar transition state. And that makes it also a challenge in ammonia decomposition to form those nitrogen molecules. The other challenge would be the dehydrogenation of the ammonia molecule, which is like the early barrier that needs to be considered, and then the late barrier in the mechanism would be the nitrogen recombination.
Yeah, those barriers are important. And to have the most efficient round trip, basically from hydrogen to ammonia to hydrogen, we want those barrier to be the smallest, and therefore the best catalyst available. Now we talked about iron and cobalt, but there are also other metals. And one metal which is also very good at this reaction is ruthenium, right?
Yes.
And there it is very prone to react with nitrogen.
Yes. So it is not about to be to form the strongest bond to nitrogen, but in catalysis we have this famous Sabatier principle, which says that you need an intermediate interaction of the surface or of the surface atoms to the intermediates, because if it's too strong, let's say, then the following steps will become rate determining, and if it's too weak, then the formation step of that intermediate would become rate determining. And this is the famous volcano curve, where there's two sides. Typically, you come from a side with too strong binding, you get to the peak where you have the best compromise, and then it goes down again. The rate goes down again if your binding becomes too weak. And ruthenium happens to be very much at the peak of that volcano. So it has just the right binding energy to nitrogen in order to be very active in both reactions, ammonia synthesis as well as ammonia decomposition. It's also more active than the iron catalyst in the Haber-Bosch case. But of course, iron, it's more or less an ideal catalyst, because iron is the cheapest metal you can imagine. And there is a huge, several orders of magnitudes, I don't know exactly, price difference to ruthenium, which makes, although it is the better catalyst, makes it uneconomic to use it in such large-scale processes.
Yeah, definitely. I also used ruthenium in my PhD research for amine synthesis. So it's also this nitrogen compound in there. And there it was also always the challenge that, you could find a very great catalyst, but to bring it to the industry, ruthenium usually is too expensive. And that is also, I think, what's the case for this reaction. Maybe for this small scale reactors you mentioned before, the ruthenium catalyst, because you don't need as much, might be viable. But if you want to do it on large scale, you need huge amounts of catalyst, and then ideally a cheap catalyst. And then, the iron would be ideal, but it's not as reactive. So you looked at combination also with different metals. Was it just cobalt, or what was your approach here to gain understanding from trends, as you said before?
Yeah, it was, first of all, it was a bit inspired by this volcano curve that I just mentioned. So if you look at it, then you will find iron on a bit too much. It's near the peak, it's good, but it's a bit too much on the too strong binding side. And then you can look on the other side, and in a very simplified or in a maybe simple approach, you would just say, okay, by allowing you combine the properties of the two. So we would need to look for something at the too weak binding side of the volcano with a similar distance to the peak, and then you immediately would find cobalt there. And then also you can, if you look at the phase diagram of the two, they alloy quite easily. That's of course also an important aspect. So we could also vary the iron to cobalt ratio in these bimetallic catalysts. And what we found, and that was a very nice result, is that we can really kind of describe that peak of the volcano, right? We start from pure iron, we end at pure cobalt, and in the middle, at the 1-to-1 ratio, we found the highest activity. And if we have less cobalt in, then we are in between that peak and the iron position on that volcano. So that, simplified view, it seems to be true to some extent, and is also nothing that we invented. But it can be applied on the iron and cobalt case for ammonia composition with very nice results. And that was also what our theory colleagues could confirm. So kind of you climb from the iron position to the top, towards the top of the volcano, by alloying or putting in just the right amount of cobalt, moderating the too strong binding to nitrogen, make it a little bit weaker, but not too weak.
And how does this combined iron-cobalt catalyst then compare with the ruthenium?
Yeah, I think it's not orders of magnitude less active, but it is less active. So it's not a substitution for ruthenium. Yeah. But what we could do with this catalyst, and of course you can look at activity from different perspectives. In academia, typically we are interested in the activity per active site or per surface metal. And there ruthenium, I think, still is unbeaten. But what we can easily do with those with those cheaper and more abundant metals is...
Yeah, it should be orders of magnitude cheaper, right?
Yes. And we can increase the loading. And you probably know that the Haber-Bosch catalyst has an extremely high iron loading. It's around 90%. Like a typical noble metal catalyst, like a three-way catalyst, for instance, or also anything that you would think of about ruthenium, would be loading on the order of 1 or 2%, because
the price,
it's so expensive, and it's like weight loading, and you pay by weight, right? But with those cheaper metals, what we can do is we can easily, if we manage to synthesize them correctly, we can easily increase the loading to, in case of Haber-Bosch, to 90% or something, and still have a large metal surface area exposed, right? The fraction of surface atoms compared to those in the bulk that are not used in catalysis is really bad. But the total number of surface metal atoms is not so bad. And so you would never be able to do this with ruthenium, right? You cannot use ruthenium with a, say, 50 nanometer large particle, which is, you can just not afford to not use all of that ruthenium that is in the bulk or in the middle of that particle. But with iron, and also with iron-cobalt, you can simply do it. And so we have, and there was like a special synthetic strategy that we are also looking a lot at. We are using quite high loadings, so we have more than 70% of metal loadings, and only like 30% of roundabout of typical support material. So those catalysts really look like a metallic sponge more than a typical supported system, where you have an extended porous but inert material where you have very small nanoparticles of noble metals. And that allows to increase the number of surface sites per reactor volume, right? Typically in large scale production, you have a certain, you have a large investment to create that reactor. It has a certain volume, and you need to fill as much surface atoms in there as possible. Yeah. And it's not so important if you don't need to pay for them a lot of money. It's not so important whether you also fill in bulk atoms. So in this case, we can gain something in that comparison with ruthenium, not by the high activity of the single surface atom, but by the amount of surface atom total amount that we can load into such reactors. And that's also what makes these more base metals interesting in heterogeneous catalysis, or interesting for us. Also looking at the synthetic challenges, how do you stabilize them at very high loadings? So what you do not want is, of course, that they sinter to one large metal blob, whatever.
Yeah, the porosity is very important.
You need to somehow have the porosity and stabilize the porosity, but you don't need necessarily to work with 1 or 2 nanometer small particles for that.
So look at the properties of the whole catalyst setup in the end and not just the active site itself, so that you optimize for the most efficient reaction process rather than just looking at the single site catalyst.
Yeah, I would say so. It's a bit a shift of the perspective, maybe, right? It's not so we're not doing process optimization or anything. It's all on the catalyst, but it is also important how the catalyst formulation is synthesized in order to compare catalysts. It's not iron equals iron. I can make a very bad and a very good iron catalyst. I can do the same with ruthenium. And unfortunately, it's very easy to make it bad. To have this high porosity with a high exposed metal surface area is sometimes challenging. And it has a lot to do with inorganic solid state chemistry. So I come back to what I said in the beginning. That's some aspects that are needed in order to be able to stabilize these porous sponge-like structures that we aim at.
Yeah, and also the synthesis has to be somewhat easy, because that's also one of the problems with homogeneous catalysis that I did, that you have sometimes very difficult to synthesize ligands and they are very expensive to make in large scale. But when you are in the solid state chemistry, sometimes the process is easier, but as you said, it's difficult to get the exact right pore size and exact right structure of the solid. So you developed this synthesis method for this iron-cobalt and magnesium oxide. I think, would this be relatively easy to do also on larger scale?
Yeah, at least I think it would be more facile than most things in molecular catalysis, which are, of course, very, very important catalysts. And you have, I always, of course, I'm a bit jealous that you can characterize your metal surroundings so good and that you can count your active sites so good in molecular catalysis. This is all big problems in heterogeneous catalysis. But you're right, the scalability of the synthesis and scalability also in means of reproducibility and in particular also cost is probably easier in solid state or in heterogeneous catalysis. And of course, there are many examples. As you know, heterogeneous catalysis are industrially have a wide field of applications, and so their manufacture seems to be under control. There are industry can do this, can provide those materials, but of course, you want the synthesis to be ideally aqueous. No other typically more harmful solvents involved. You want to have it as little steps as possible. So if it's a 20-step ligand synthesis that you need to do, that's probably prohibitive for an application in the end. This, of course, is not true for applications like in pharmaceuticals. No problem, probably, because the cost of the product justifies also that the catalyst can be expensive. But for these, energy relevant base materials, that is certainly an aspect. So what we're using mostly is a method that is called co-precipitation. And I always explain it's like the invert of what most people start with when they study chemistry. Because at least in Germany, what people do a lot is they look at aqueous separation of ions. They want to separate the sulfides, for instance, in order for analytic chemistry. And now the target is exactly the opposite. You have two ions and you want to bring them together in one solid, right? You don't want to dissolve your solid and separate it, but you want to bring them together in one material. And that's what we do in co-precipitation. So, for instance, as you mentioned, we have iron and cobalt, which we have already discussed to be the active phase. And then we in the final catalyst. And then we have these lower amount, like this 30% or something of magnesium oxide in. Magnesium oxide would have the function as the support, stabilizing the metallic nanoparticles. And in order to obtain small particles of both the support component as well as the metal component, we need to intermix them as good as possible. They should, ideally on an atomic level, they should be statistically distributed, because in the end, we will segregate them, forming metal from the one part and forming the oxide from the other part. And in order to limit that process to happen only on a very small scale, they need to be interdispersed. And that's what we can do with co-precipitation by adding a precipitating agent to a mixed solution of all the components that are important, that we want to have in our catalyst. And then we get the catalyst precursor material.
Yeah.
And that is itself not necessarily porous. It can be a well crystalline material, not in all cases, but the porosity then develops when we, in subsequent steps, decompose those. So it's also multiple step synthesis. We co-precipitate the precursor. We first of all then typically calcine the precursor. So the precursor could be a hydroxide or a carbonate that you can calcine and decompose into the oxides. Then you have already an intimate mixture of the oxides. And that is a step that typically, that would be the stage where you also purchase catalysts. It's typically the calcined version. And then only in the reactor itself, an applied catalyst is reduced, or at least the components that are noble enough are reduced to the metallic state. In our case, that would be iron and cobalt, and the magnesium oxide obviously would stay in the form of the oxide. And that is where the actual nanostructure or porosity of the catalyst is formed, because then it determines to what extent do those metal particles grow. And what you want in the end is that they are kind of in an alternating fashion, always metal oxide, so that the oxide acts as a physical spacer between the metals, preventing them from further growth.
Yeah, in one of your papers, there was a picture where it shows that it forms somehow of a mesh, and then you have also for direction later on a way for the gases to diffuse through the catalyst.
Yes, this is more a schematic picture, but this is really how we envision that, right? That we have the larger metal particles that are separated by smaller oxide particles, but in between there are pores. And it's the pores of that size that we need is in the mesoporous range, so that we get transport of gases through those pores. And on the pore walls, we have these larger metal particles. And of course, the scheme of the mesh is not as ordered, obviously, right? We have not all the particles have exactly the same size, but we have a still relatively narrow and unimodal size distribution. And I always like these drawings in order to also make the difference clear to a typical supported catalyst, where you would have the porosity only from the support, and then the metal in the pore walls, or on the pore walls. And here, the metal particles, they themselves make up the pore walls to some extent.
Well, that's a big difference to the ruthenium catalyst, where it's mostly the support, right? Yeah.
Exactly. For ruthenium, you would want to have small particles. Maybe 1 nanometer is not good, because there's also a certain particle size effect that is known for ruthenium. But let's say 3 nanometers is something where you find high activity. But then you don't want them to grow larger. You don't want them to form extended structures, because all that would mean that there would be ruthenium atoms that are unused in the bulk of those larger particles. And for iron, we simply don't care too much. And we can make the pore walls, we can create them from the iron particles because it is affordable.
Yeah. And when you also on the synthesis part, then to create this, you need a very well dispersed precursor. Otherwise, you get some big metal clumps in one part and just a lot of oxide in the other part. And ideally, it should be well dispersed.
Yeah, I said dispersed, but maybe dispersion is not the right term here, because in the precursor we can live with what we call a solid solution. Right? The dispersion in catalysis typically is referred to as the fraction of surface atoms versus the overall amount of atoms. And there are other definitions in colloidal chemistry of the dispersion that are more on a particle basis. But here we can have one large particle of let's say a mixed hydroxide. So we have iron, cobalt, and magnesium in one hydroxide phase, and we have a large particle of that, and that is a solid solution. And the surface area doesn't necessarily need to be high, but when we calcine it to the oxide and then reduce in a subsequent step the metal fraction, this larger particle can, and that's more like a top-down structuring. The previously larger precursor particle can create smaller pores in itself. It will fall apart is not the right word, because we want it to be mechanically strong. So it does not fall apart, but it becomes porous in that process. And that is because when we decompose the hydroxide, we of course emit water from it. The water has to go from somewhere. It leaves pores, it leaves void spaces that are all important in order to create those pores in the final catalyst that we want in the end. So those precursors are solid solutions of all components that we need, meaning that they are statistically distributed well, and the porosity is developed in a, well, maybe top-down subsequent step from those precursor particles.
Oh, interesting.
And it's also, I think for reproducibility is also a good thing, that because the crystallinity of the precursor is of course a certain thermodynamic sink, right? When something crystallizes, first of all, you can characterize it very well. And also if you repeat your synthesis several times, you can be more or less sure it will find that local thermodynamic sink during the synthesis. This is a bit different from colloidal approaches, for instance. And okay, they are larger crystals, but you can live with that because not you, but in kind of a self-assembled manner, they will be nanostructured in the subsequent steps.
Mm-hmm. So also for the synthesis part, the reproducibility with your approach is more easy because of you using a crystalline structures to start with and then creating a mesh from that. Yeah, very interesting. So what would be then necessary to use this reaction in a larger scale, or what do you think is the biggest challenge now to scale up this process?
Yeah, well, I mean, for the overall scenario, ammonia becoming an energy vector, probably the bottleneck is, and we are again on the synthesis side, the bottleneck is to provide green hydrogen for a green Haber-Bosch, because in the end, that is, I mean, we're not talking about gray or fossil-derived ammonia in the end. Well, a scale-up of that process only makes sense if there is green hydrogen around, and green ammonia. And we make ammonia on a megaton scale, but it's not green at the moment. And that, I think, would be like for the overall scenario is what is needed. So we need to work on a cheap source of green renewable hydrogen. And that, I think, is also technology-wise not such a huge challenge. We need to convert the normal Haber-Bosch to a green Haber-Bosch, which just means replacing the source of hydrogen, not from steam reforming of natural gas, but from water electrolysis.
Yeah, the reaction itself should be the same, but the process is so well integrated with the natural gas and the cracking of the natural gas, and it's to separate the synthesis from the rest of the process might be a challenge there.
Yeah. I mean, the most efforts, I think, and I'm not an expert, but from my knowledge of an ammonia synthesis plant, the most effort is creating the syngas and purifying the syngas. The Haber-Bosch stage in the end is probably, the efficiency is high on that stage. And the nice thing is, we would only need that stage for such a green ammonia idea. But of course, we would need to replace the rest, and probably purification in water electrolysis is also not so much of a challenge. I guess the hydrogen is less contaminated compared to hydrogen from fossil sources. But of course, the electrolysis itself is something that is also, as we know, technologically possible, but not scaled up yet. And that is, I think, but also again, the beauty of the idea, because that would allow to bring that more or less existing Haber-Bosch technology stage to a site where hydrogen is really cheap. Right? As you said, the idea is to make green ammonia in order to transport it. So we would make the hydrogen, or humankind would make the hydrogen there, where we have a lot of solar power, a lot of wind power, and reducing the price. And also then all being preferable to hydrogen costs that we would envision probably here in Germany. I mean, also those, for instance, in Schleswig-Holstein, when the wind blows too hard, they shut off the wind park because the net can take up all the electricity. And one could also, and I think it's also important, one could also think about using that energy to go into something like green hydrogen or green ammonia. But of course, it would never be a 24/7 process that you would like to have if you make such investments. And that is what I think is really attractive in going to countries where they maybe are building industrial infrastructure anyway at the time of their development, and then building that type.
Make it green from the beginning.
Yes, that would allow to supply the world with cheap green ammonia. And then, of course, also we as an energy importing nation could envision new trading partners going away from fossil sources with all the political conflicts that is also there with them, and maybe have new partners, stable democracies, ideally, to get the energy from them.
Yeah, exactly. Because also transporting the electrons as electricity over large distances is not that easy. And when we have solar or wind power, that usually creates the electricity. And then this would be a good way to transport this electricity in the end from countries with a lot of solar and wind to bring it to here, to Germany, for example.
Yeah. If you consider like a fuel cell application for the hydrogen in the end, it would be exactly that, right? You would go back to electric energy. And of course, it is less efficient than a battery, but you would not ship a battery, I guess, or many batteries just for cost reasons and probably also for energy density reasons.
Yeah, exactly. And now I think we can come to an end of this discussion with the closing question: what is your favorite discovery in chemistry?
Yeah, I hope my favorite discovery is still to come in the rest of my scientific life. But so far, if I look back, I would say, and of course it's an easy target now, I would say indeed like the development of the Haber-Bosch process. Because it's also like a blueprint in a way, and you also addressed that in your podcast episode. Mankind was also faced like a global problem, right? Feeding the world at the dawn of industrialization, the need for replacing the natural fertilizer with artificial fertilizer, and chemistry solved that. And I think that's still a very beautiful solution, which now can become relevant also to energy supply, not also to food supply. And I think it's a great story of success for chemistry and for applied chemistry. And of course, there are several other very important developments, but now I would choose that one.
Yeah, great. That's also, as I said before in the previous episode, my favorite discovery in chemistry. It is really transformative for mankind and made all these humans that we have today on the planet even possible. So it's a very important discovery. Yeah, thank you very much for this insights in your research, and very interesting for me to learn about these catalyst syntheses. Yeah, thank you.
Thank you. Yeah, I enjoyed it a lot, and thanks for doing this with these podcasts. I think that's really nice to see that you address, or that I can address, chemists as the major audience with what we're doing here. Thanks a lot.
Also, thank you for listening. You can find links to Malte's publication in the show notes, and don't forget to follow Innovate and React on wherever you get your podcasts. Until next time, keep innovating and stay curious.